So I start sharing with you our experience on the modeling steered chemical and biochemical reactors in the realm of computational fluid dynamics. My focus will be mainly on 2 and 3 phase flow and on the capability of computational techniques to catch the physics of this system, because clearly starting from a correct prediction of multi-phase flow, we are sure that we are able to well predict the heat mass transfer and chemical reaction that definitely will affect the reactor performances. We have a number of different computational methods available nowadays that have been developed with the support of experimental data for validation, and we can find enormous amount of investigation on the simulation of solid liquid and gas liquid mixing in turbulent steel tanks. This is clearly a topic that can be faced at a different level of detail, but since our target is to scale up industrial reactor, we have a specifically targeted to have a robust tool in order to obtain sort of satisfactory prediction, but without model calibration. But also we need to have an industrially viable tool. So we selected the Reynolds average Navier-Stokes 2-fluid model because it is affordable for complex geometry, large-scale equipment, and also it can tackle high loadings of the dispersed phase. Modeling target are basic quantities first, because if we don't get these fundamental quantities right, we cannot predict reliably the reactor performances, and this has to be achieved at any scale and at any geometry. In the realm of the Reynolds average 2-fluid model methods, we have to deal with 2 main challenges. One is clearly related to that arise particularly when we have a phase segregation, and we have also, of course, as main task to identify closure models for turbulence and for phase coupling. Both these aspects are crucial for obtaining reliable prediction, and even though a lot of work has been already done on this topic, methods for tackling these 2 challenges are not universally valid, because depending on the geometry of the reactor, we can have different problems and different strategies and different modeling challenges to face. Here I show you just a couple of examples of steered vessels with the non-conventional geometries. In this case, we have an impeller that is off-centered with respect to the axis of the vessel, and in this case, the steady solution that typically works well for standard geometry vessel doesn't work. And in the other case, we can see that very wrong prediction of the solid distribution in an unbaffled steered tank if we use chaos epsilon family models instead of Reynolds stress turbulence models. So just a couple of examples for saying that even though this is a topic that has been depending on the specific geometrical configuration, the multi-phase flow dynamics inside changes quite a lot, and we cannot generalize the models and the numerical solution strategies in all cases. One aspect that I want to stress particularly is also the importance of the spatial discretization of the computational domain that is already important in single-phase flow, and it becomes even more important in the case of 2-phase flow. Here you see that increasing the grid size, we can, in the case of a steered tank in a single-phase flow, get a very close prediction of the power consumption that is summarized here in this power number, and we can decrease quite a lot the numerical error, also by looking to the spatial to the discretization of our partial differential equation. So something that is often disregarded in the realm of the Reynolds-Navier-Stokes method is the numerical aspects that actually is less important for the mean variables, but becomes particularly important for the turbulence variables, which affect, particularly in the case of liquid, gas-liquid system, actually the distribution, the size distribution of the dispersed phase. So it's the reason why I'm stressing these aspects now. So what we can do for going on and use CFT methods based on the two-fluid model for scaling up and down steered chemical and biochemical reactor. First of all, we have, as I mentioned before, be particularly aware of the difficulties in case of unconventional geometries, and if it is the case, it's better to have guidelines for experimental observation. In case of conventional geometries, we have a high amount of data and correlations that can guide us in the identification of the right modeling approach. Experimental observation at lab scale, of course, and among others, I show you examples of how we can get information on particle-particle interaction from solid distribution at equal impeller speed and variable mean soluble fraction. For instance, we can get information on fluid-particle interaction from liquid mixing time measurements with and without the dispersed phase in the liquid. Gas at power consumption and gas-liquid flow regime are also particularly important to know in advance for evaluating the reliability of gas-liquid modeling for steered bioreactor, for instance, that are widespread in the case of the fermentation industry. We can also have guidelines from production issues at industrial scale, and I'll show you an example for that. Starting from the simplest of the system that I selected, the solid-liquid systems, we can already see that is a case of strong complexity in terms of the physics that we have to describe, because in a steered tank, a steered reactor or bioreactor, we can have, depending on the solid loading and impeller speed, have a very wide distribution variation of the dispersed solid phase. And so we are in a condition to have in some region one-way coupling between the two phases, in other region two-way coupling. And we can go even to four-way coupling, and in the end in granular flow, depending on the regime. Actually, depending on the region of the vessel, depending on the impeller speed, we have solid on the bottom of the tank that is steady, that is unsuspended. In this case, we have a granular flow, while moving far from the bottom of the vessel, in the case of heavy particles, of course, we can find all the other situations. So we need a model that is able to tackle this complexity, to include all these physical effects all together. And we have also to consider the effect of turbulence, of course, on the dispersed phase distribution. We need to take into account the interface momentum transfer. So drag and turbulent dispersion force are typically the major contribution in these systems. And we we should be able to account for the turbulence modulation effects due to the particles, we need to consider how to model turbulence for the solid phase. So on the modeling side, even though the solid-liquid system is relatively simple with respect to gas-liquid, for instance, because we have a fixed size of the dispersed phase, we have a lot of challenges to face. I selected here a case of a solid liquid system, glass particles in water. In these figures, you can see the results of a simulation where we adopted different formulations for the two main forces, two main interface momentum transfer contribution that are the drag and the turbulent dispersion force. I selected this case just to show you that very small variation on the model equation that seems to be not so relevant. In this case, you see that the drag force and the turbulent dispersion force are written considering both the volume fraction of the two phases or just in some cases adopted, and the CD, the drag coefficient, is another critical variable that we need to fix. And depending on the way we formulate these two forces, we can either have solid on the bottom, that corresponds to unsuspended solid, or fully suspension of the solid. So it seems a small difference, but of course it makes a big difference when we have particles accumulation, because action, the forces are limited by the combining effect of the dispersed and continuous phase volume fraction, while if we use just the solid phase volume fraction, we have a monotonic increase of these forces. So when we set a simulation, when we formulate our model, this way to write down the forces is a critical aspect. If we neglect, for instance, the turbulent dispersion force, we have a totally different picture. So instead of having just a small amount of solid on the bottom, we have a huge amount of unsuspended solid. So you see that this model formulation is critically dependent on the way we formulate the interface momentum transfer term. Another aspect is the selection of the drag coefficient correlation. We have a number of different correlations for the drag coefficient in still of particles or bubbles in still fluid, but we have to be aware that the drag coefficient changes due to the effect of the turbulent flow. We have correlation in the literature. One of these correlations comes from our group, but actually the adoption of this correlation can be not necessarily depending on the range of power dissipation that is in our system that affected the Kolmogorov length scale, and that actually, as compared with the particle diameter, produce different effects. So here again an example where we can see that in this particular case we don't have effect due to the turbulence on the drag coefficient, but we have a huge effect of the turbulent dispersion force. Now I'll show you a few comparisons with the experiments. Provide the idea of the capability of our model to catch the features of this two-phase flow. What I want to also address is the fact that if we look just to one variable for doing validation, for instance, the height of the liquid, solid liquid suspension, we can actually get not a good evaluation of our predictive capability because this solid liquid suspension level can be predicted in the same way by simulation, where instead we have a very different distribution inside the suspension of the particles. So actually we have to know the local solid concentration distribution in order to be sure that our predictions are reliable. And to do so in systems where we have a high volume fraction of the dispersed phase, we can adopt, for instance, electrical resistance tomography, that is a suitable technique for looking inside solid liquid suspension without being intrusive. provided that we are far from the interface where the so-called fringe effect makes the ERT measurements not reliable, we can trust on these measurements. And for instance, when I mentioned you before, having guidelines from experiments for modeling, I mentioned I was had in mind, for instance, the fact that if we measure the solid concentration distribution, increasing the volume fraction of the particles, and we see, as in these two examples here of radial profiles of dimensionless concentration, that our profile are more or less the same, are practically not affected by the increase of the volume fraction, it means that we can neglect the particle-particle interaction in our simulation. In this case, in this particular system, up to 15% of solid particles actually produce the same dimensionless concentration distribution locally. So this is an important observation for guiding our model formulation. In the end, if we look at the capability of the modeling choice to reproduce the experimental solid distribution inside the vessel locally, we see that there is a very good agreement, both in the case of an impeller speed that is below the NJS, that is the just suspended impeller speed, the minimum speed required to suspend all the particle in the vessel, and the same happens when we have a volume impeller speed that is above this NJS. So we can get a real picture of the turbulent solid-liquid suspension in a complex geometry and with high volume fraction of the relatively high volume fraction of the dispersed phase without any model calibration. This is particularly important because if we want to use this modeling method as a design tool, we need to be sure that it is generally valid, and we don't need any parameter to calibrate to get the results. We can have also a very good idea on the physics of the solid-liquid reactors, measuring the mixing time, the liquid mixing time. You see here, we obtain typically this transient dimensionless conductivity curve by ERT again, injecting a small amount of salt solution. You see here the conductivity on the 4 horizontal planes of the vessel without action. We have a uniform conductivity, of course, because we work in under state condition. Then if we inject a pulse of salt solution, we see this red color here that represents the salt that is coming inside, and in the evolution in time will lead us to have again a uniform concentration, uniform conductivity inside the vessel, but of course the level of conductivity with respect to the initial value is different, and you see a red color instead of blue because we have increased the concentration due to this pulse of salt solution. If we obtain the time trace of this dimensionless conductivity in a plane, making an average, you can see that here we have a huge difference in mixing time. That is the time required to achieve the complete homogenization of the vessel, depending on a single orthophase flow condition. Clearly, the solid particles in this case make the time required to obtain this complete homogenization much slower. And this is a characteristic that is very important to catch by computational fluid dynamics simulation, because of course in a reactor, the time required to a reactant to distribute inside the reactor is particularly important. This is a feature that depends on turbulence again. So if we want to catch this, reproduce by computation this experimental observation, we need to solve transient scalar transport equation, where we have again a modeling requirement due to the fact that the turbulent dispersion of the tracer depends on the turbulent diffusivity that we need to model. So we have to rely on a turbulence model also for this term, and provided that we are able to reproduce well the turbulent kinetic energy dissipation rate that affect the turbulent viscosity, you can see here from this comparison between experiment and CFD that in single phase flow we have an excellent agreement. Details on these are also given in this paper below. I don't have time to go into each detail, but what I want to stress more here is that we have a very good agreement not only in single phase but also into phase flow, and provided that we have a proper turbulence model formulation. We have in this case issues related to the fact that we have to consider the effect of the dispersed phase on the turbulence of the liquid phase. So depending on the two-phase model formulation, we can get a different level of accuracy of our prediction. But again, without model calibration, with a suitable selection of models and a suitable refinement of our computational grid, which affect quite a lot the turbulent dissipation rate and therefore also the turbulent dispersion of the tracer, we can get a reliable picture of the system. More challenging is the case of gas-liquid steered vessels, which application, as I mentioned before, for instance, in the pharmaceutical industry is significant because a lot of molecules are produced by aerobic fermentation, and aerobic fermentation, of course, is affected by gas-liquid mass transfer, which is often the limiting step for this. And of course, it's very valuable for scaling up industrial fermenters, for instance, among others, but also chemical reactors where mass liquid, mass transfer, chemical reactors take place. Is particularly important to be able to predict well mass transfer and liquid mixing time. Here I show you an example of wrong scaling up in lab at 5 liter and 20 liter. The KLA is taken from an industrial aerobic fermenter and a preliminary investigation in the lab. The company considered possible to have a good productivity in this reactor based on experiment at 5 or 20 liters, so in the lab on the pilot reactor. But moving to 40 cubic meter industrial production, the situation went much worse than expected. Why it happened? It's easy to understand actually this behavior if a detailed fluid multi-phase flow dynamic knowledge is possible. And if we look to the classical flow map for a seeded fermenter, we see that moving from a small to large scale, the gas-liquid flow regime moved from recirculation to flooding. And of course, when the impeller is flooded, the bubbles are not well distributed in the vessel volume, and the KLA drops dramatically. This is just an example for highlighting the importance of having a deep knowledge on multi-phase flow dynamics in steered biochemical and chemical reactors, because sometimes fluid dynamics is disregarded, but of course is the fundamental aspects to look at. So why I say that gas-liquid systems are much more complicated is obvious, because we don't know in advance the bubble size distribution. So depending on the assumption that we perform on the bubble size, we can get a totally different picture of the gas liquid fluid dynamics inside the system. You see that moving from 1 to 2 millimeter of bubble size. This is a simulation where we fix the bubble size. We don't have prediction of the bubble size distribution, but we limit to a modest assumption for starting and for checking if we are able to catch well the at least the two-phase fluid dynamics, and we consider then the population balance modeling for predicting the bubble size distribution. So if we assume a millimeter size, we have this distribution with a high volume fraction of the dispersed phase of the bubbles in a slice of the reactor. If we go to 2 millimeter, the picture is totally different, and instead when we go to 3 and 4, the picture is totally equal to the case of 2 millimeter. Why did it happen? It's clearly because when we have this two-fluid model as our model, we know that the drag and the turbulent dispersion force depends on the drag coefficient. The drag coefficient of bubbles exhibit big changes moving from 1 to 2 millimeter, while when we are above 2 millimeter, a few millimeter more, we have a slight variation of the bubble rise velocity. Is indeed the bubble rise velocity the variable that have to look at. The bubble size is actually useful only for calculating the drag coefficient of the bubble rise velocity. So this is crucial. This is a crucial parameter. Why? It is crucial because from the bubble size we can get then the mass transfer. Actually, we have the prediction of the mass transfer coefficient. Should we have experiments for guiding us in the determination of this KLA, we have actually in this field an extraordinary work done experimentally by Professor John Smith and Professor Alvinino in the past, who derived very important correlation and very important knowledge on the physics of this system. And so they came out with the fact that KLA, the volumetric mass transfer coefficient, depends on the turbulent dissipation rate in the gaseous condition, and in superficial gas velocity that depends on the gas flow rate. We know that there is a huge uncertainty in the calculation of this KLA because this constant actually depends on the composition of the liquid phase. If we have antifoam or surfactant, KLA is lowered. If we have a salt, this KLA raises, because actually these agents, these chemicals change the composition and change the tendency to coalesce and break up of bubbles. So having the capability to introduce these physical aspects inside the run simulation is currently not possible, and in this area it's very interesting to go to multi-scale modeling, looking at the bubble size simulation first, and deriving information from this bubble size level simulation, possibly by DNS simulation, and moving to the runs. But okay, provided that we are at the vessel scale, we can rely on correlations for bubble size in order to start our simulation, and having a methodology that can start from a bubble size that is predicted by correlation and moving further on, as I'll propose you in a few minutes. We want to use a single bubble size at the beginning of the simulation. We don't want to go directly from coupling the two fluid model with the population balance model, because the fluid dynamics inside the gas liquid reactors is very complex. We know that we have a cavity on the rear of the blades, depending on the shape of the blades, particularly when we have flat blades. This effect is very important, and we need to take into account this effect. We need to be able to predict this effect, to have realistic prediction of the bubble size distribution, because bubble size distribution affect KLA, and bubble size distribution is affected by the power dissipation, which depends also on the cavities. We are able to reproduce the cavity. As you can see in this picture, we have gas accumulation, and we have a realistic picture of this. And from this gas accumulation, also the regimes inside of the reactor depends. Here we have a full recirculation of bubbles everywhere. We have a loading condition in these two cases. And in this case, we have a flooding condition. And so if we can get the cavities, we are also able to get the regimes for the bubbles. And as soon as we have this very reliable gas liquid fluid flow prediction, we can go into details and look at the mechanisms that lead to power consumption reduction. That is very well known, that has been observed experimentally in the past, but was not well predicted until a few years ago. And we can then have a local picture of how the gas is dispersed. And if we add the mass transfer and chemical reaction kinetics here, we can actually predict in a very detailed way what is the capacity of the reactor. As for the KLA in detail, we can of course predict KL as a function of the turbulent dissipation rate based on the literature correlation. We can go to calculate in an approximate way the interfacial area between the gas and the liquid phase. This is a way that we propose to adopt in a simplified and fast way without moving to population balance modeling. This summarized in this paper that I reported on the bottom of the slide. So if you are curious, you can have a look to the paper. But of course, the most reliable way and the most complete way is by population balance modeling. It is very computational intensive, going to population balance. And so just a word to say that we have to be aware of the importance of having a mesh also into phase flow that is fine enough. Our suggestion is to refine locally close to the impeller, because we can use actually a coarse grid just out from the impeller, and the prediction accuracy doesn't change a lot if we have just a locally refined grid instead of refining all the computational domain. It seems obvious, but these aspects can save a lot of computational time. I must say that actually before going to predict mass transfer, actually we need to consider that it's better to my experience to get a good prediction of the two-phase flow dynamics and then move to the population balance, as already mentioned before. So balance models, we should be able to predict gas segregation right at the beginning, but since bubble size depends on the local turbulent dissipation rate, this is a very critical aspect to address. When we have these bubbles going out from the sparger, do they affect the bubble size distribution prediction? What we notice is that depending on the regime where we are, if we are in the loading regime with cavities, we have a very critical situation, and coupling directly the fluid dynamic and the population balance equation actually do not lead to good prediction in many cases, unless we perform molecular calibration, and that's another story. In a fully recirculation regime, it's much easier to get a realistic prediction. So I want to show you some results in a specific case. In this case, we have the prediction obtained by a population balance simulation with the appropriate recalculus and the quiescence kernel, of course. We have a very bad prediction of the bubble size in the impeller zone. We have a good prediction of the bubble size far from the impeller. And this is related to the problem of the cavity and of the problem, the two-phase turbulence model, where gas segregation takes place, that I mentioned already at the beginning. So it's a challenging system, but we can manage to have good results looking at the regimes and looking at the distribution of size, but also to the distribution of the bubble rise velocity. Because in some cases we have a wide distribution of bubble size, but a narrow distribution of the bubble rise velocity. And in that case, we can simulate the system with a monodispersal assumption. Instead, if we have a wide distribution of the bubble rise velocity, we cannot avoid having a coupling between the bubble size and the fluid dynamics. And indeed, we need to perform simulation coupling CFD to fluid model and population balance. So for going towards the conclusion, our idea in adopting CFD methods for scaling up and down steered bioreactors is to consider a workflow where we start with purpose of simulating in a right way the gas liquid flow fluid dynamics. If we have a standard geometry, we can rely on the knowledge that is available in the literature that is based on experiment and makes us available correlation. And we can start from these correlations for having a first guess on the bubble size and assuming a monodispersed distribution, we can get a gas liquid flow field with a single bubble diameter that typically is reliable if we have a standard geometry and reliable correlation for the south diameter of the bubbles. If we don't have a standard geometry, so we have unconventional geometry, we need to go to a more complex methodology that can be a little bit more time consuming in terms of computational time, but it's viable. We can start from a single phase flow simulation that produce reliable results for sure if everything is done properly. Then we can solve a Lambda parameter population balance equation. So we take the turbulent dissipation rate from the single phase flow simulation, we solve a population balance equation using that value of turbulent dissipation rate. In this way, we obtain a first gas distribution of bubble size, and we can see if from this distribution we have a narrow or wide distribution of bubble size. If the distribution of bubble size and terminal velocity is equal to the initial gas and the calculation converge, we can go on, or we can consider the solution as it is. So this is a way to face the gas liquid flow field, to have a good prediction of the gas liquid flow field based on a monodispersed assumption of bubbles, but of course we cannot stop there. We need to go on, and we need to predict mass transfer rate, and in this case we need to couple population balance with the two-fluid model equation. And at the beginning, we can start from the solution of the flow field obtained with a single bubble size that we obtained, as I just told, with the monodispersed assumption in the two cases as before. We solved the coupled population balance solution, and we analyze the volumetric distribution of the southern diameter. If the bubble size is monodistributed, we actually are close to the solution. If not, we need to run coupling between population balance and two-fluid model. And instead, if they are not coupled, we can solve just the population balance and obtain a reliable solution. So in this way, we can reduce the uncertainties in the direct coupling that makes problems when we have gas segregation, and at the same time, we can achieve a faster solution because it's also important in the case of industrial application to limit the computational time. So this leads me to conclude this talk. In summary, if we have the target to scale up and down chemical and biochemical reactors, Reynolds average methods to fluid model are a viable solution nowadays, much more reliable than traditional methods based on global parameters. Clearly, since we are in a very complex physics to describe, because of turbulence, because of two-phase flow, because typically high volume fraction of the dispersed phase, clearly we can have also solids and bubbles and droplets in the same reactor. So I limited the attention to two-phase system, but it's not always the case. In many situations, we have already experimental references. In some other cases, particularly for non-conventional geometries, we have not. And since the physics is very complex, in order to lead to obtain reliable results, we need an appropriate model formulation that has to be guided by experiments. Since we have the need of closure models and correlations, we need to be very careful to check the validity of these correlations with respect to the investigated system condition, because in many cases issues can arise from the wrong adoption of a model or correlation out of the range of validity. And our main aim in the research is to devise methodologies that can be reliable without model calibration. So typically for safe adoption of these runs-based models for scaling up, we suggest to scale down to perform a scale down with respect to the production reaction that we have in mind, or a company have in mind. We characterize the scale down system. This is an example of the application of a biogas digester. So that is a very unconventional geometry with free shaft and slurry with the non-Newtonian behavior, so in that case it's even more complex. And then we can perform a validation at lab scale and scale up to the industrial scale. With this, I conclude. I thank you very much for listening. For additional information on our group, we have this webpage where we summarize the expertise of also my colleague Federico Alberini, Nicodemo Di Pasquale, Francesco Maluta, Alessandro Paglianti, who are of course co-authors of all these results that I just showed you. And with this, I hope that everything was clear and that you have questions.
Yes, thank you. Thank you very much, Professor Montante. Thank you, Giusy. A very nice talk, very informative, instructive also. I liked very much your way of giving advices to people, despite looking at highly complex systems, including multi-phases, of course, but not only from the hydrodynamics point of view, but also transport phenomena, and the changing shape of this first phase. Very, very, very interesting. It's time now for the discussion, for questions. I forgot, and I apologize for that. I forgot to mention Professor Jun Yao, who is actually the true organizers of all these meetings. I'm just sharing this. So thank you, Jun and Professor Yao, for all that you're doing that here. And now the talk is open for discussion. We have already a few questions in the chat, but if there is anyone willing to ask live, we can take one. If not, I'll read the first questions coming from the first of a few questions coming from the chat. And the first one is coming from Professor Yao. What's the meaning of granular flow? I think you showed in one of your slides with the stars, with the asterisks. One part was referring to granular flow. Does it refer to dense flow? Was this the meaning of granular flow? Please.
Okay, thanks a lot for the question. Yes, indeed, I was too fast. Actually, I was referring to the case where the interaction between the particles prevail with respect to the interaction between the particles and the liquid. So in the realm of a two-phase flow model in the runs, we have this granular flow model where we have like a granular pressure that actually is a modeling method that accounts for the particle-particle interaction. So when we have particles that are unsuspended on the bottom of the tank, we have like a flow that is dominated by the interaction between the particles, and that's I was mentioning as granular flow. Dense flow can be still a system where we have prevailing interaction not only between particles but also between particles and the liquid phase.
Yes. Why I ask you questions? Because in the slides you give one-way coupling, two-way coupling, and the four-way coupling, and after that you mentioned the granular flow. So I'm thinking, it's possible the granular flow actually is connection with connections with the one phase, two phase, or one way, two way, or four way. This is why I asked you here.
Yeah, sure.
Actually, granular flow is very popular in the chemical engineering. It's very previously also using this studied problems in this numerical conveying of the granular flows. That's a gas solid flows. So this is why I like to ask you, how about this linkage between this granular flow with other two-way, one-way, or four-way couplings? This is why I ask you question. Thank you.
Thank you.
So
yes,
about please, continue
please,
your question.
Please, Jun. There is another question from the chat regarding the cases considered in the presentation. It seems complex case with complex structures, and the question is: do you simulate them by commercial software or in-house code, or combined both codes?
Okay, so the simulation in our group are performed either at the moment. I started using CFX many years ago, but at the moment we use two software. One is a commercial software, and it's Fluent, and the other one is OpenFOAM. Actually, in our experience, doesn't make major difference using one or the other. Clearly, the numerical aspects are much more stable with a commercial software like ANSYS Fluent with respect to OpenFOAM, but the most important is actually the capability to look at the equations and to select the right also numerical solution strategies. So nowadays, the stirred tanks reactor can be simulated more or less in the same way. The major difference, I think, is the CFD analyst, not the software, because it depends on the person who set the simulation. In any case, it takes a long time to have a converged solution for this system because of the complex structure that yes, you notice.
Yes,
that's very true.
Actually, why I ask you the question? Actually, the same way for us. In China, a lot of people do simulations. So different cases using different software or different ways. Some of the people use commercial software, and some people use indoor codes, and combine both. Presently, a lot of the industrial problems actually is very complex. So this is why I ask you a third question. This question actually is very. I'm thinking many people like to know what's your suggestions or comments. Yes, in the areas. Yeah. Albert. Yeah.
It's yeah.
So I continue the question asked you. Yeah. Based on just now, I asked you the questions. It's very complex problem. They considered by the simulations. So can you please provide some comments or suggestions for us or for young researchers? Yes, how quickly or how to efficiently to do the job, particularly for the industrial problem using this simulation ways. Can you, based on your long-term experience in this area? Yeah.
I'm not sure I catch the question entirely. So
actually,
the suggestion
this is maybe this is actually ask for your comments or for your suggestions for young people or for us. How to do the research very quickly, very efficiently, or to find a better way to solve some problems. Yes, to solve this complex problems in industries. In universities, usually we made some very simple problems in is very academic problems, but for this industrial problems, just actually for your presentation, we already know many different cases. Yes, different phases. Yes, 3 phases or different ways, 1 way, 2 way, or many. Yes, also using some experimental work and simulation work together. Yeah, to set up or to confirm your simulation. So we'd like to know what your experience, or just to briefly give your some experience to us, how to combine our research, our work with the industry to do it better in quickly. Yeah.
Like some advice for people who start, maybe, who is not very, very experienced and has a challenge coming from industry, for example, on a complex topic like solid liquid reactor or solid gas or gas liquid reactor. Then if you have some general advices.
I would say that the important is not to disregard the complexity and not to trust because software like they are, because nowadays there is a lot of commercial software promising that everything can be done fast and right. And so I think that we need to be aware of the complexity and of the challenges, because if we just use these computational tools for research, okay, you can understand something that is wrong and that's it. But if you apply to industrial scale up, it become a big issue. So my advice is to be very careful and to understand very well the physics before starting doing any computational work, because the model formulation has to be based on a very well understanding on the physics. So if you can do either by experiment or by a theoretical analysis, this is a fundamental preliminary step for doing a valuable job. Otherwise, it's very dangerous, I think, with the numerics to get results that are not reliable. It's easy to predict something that doesn't correspond at all to the reality. So that's my suggestion.
Something that is called, instead of computational fluid dynamics, someone calls them colorful fluid dynamics. No, it's just colorful. Very colorful.
Always very, very dangerous to disregard.
Yeah, maybe we can also mention, Giuseppe, if you agree, that sometimes, as you said, the experimental data and comparison against the experiments is extremely important, and you've shown that very clearly. Sometimes you have no possibilities to carry out your own experiments, but there's a huge amount of data available in the literature. No? So it's very, very important also to get some reference data on your topic that may guide then the simulation work.
Yes, that's exactly what I think is important. Thank you, Alberto.
I have one very small curiosity regarding the part that you've shown on the mixing time in the case without and with particles, and the fact that particles actually slow it down, the mixing property, and that was attributed to the turbulence. You mentioned the fact that turbulence was affected. My curiosity was, are you saying that the particles in that case were actually attenuating the turbulence rather than enhancing? Is that correct interpretation?
Yeah. In that particular system, with high volume fraction of the solids, we have these measurements also with the tomography that see that we have dampening of the turbulence, but also actually the mean flow field in that case is significantly affected due to the high volume fraction of the particles. So we have such a situation.
So the massive particles were actually slowing down, they dampening the turbulence effect of that the fluid would naturally have on its own. Excellent. Yeah, very clear.
Thank you, Alberto.
Any more questions from the chat or from colleagues connected or attending the talk online?
Hi, thanks for sharing your great work. Can you hear me?
Yeah,
Yes.
clear.
Yes, please.
Yes. I have many questions about, at first I asked about the turbulence dispersion, right? How you model the turbulence dispersion in your test cases?
So the turbulent dispersion arises in the case of the solid particles or or bubbles, arises from the fluctuations of the velocity that affect the distribution of the solid of the dispersed phase as well. So when we have the instantaneous drag force and we perform the Reynolds average, this contribution of the instantaneous drag force is split in two contributions, the drag and the turbulent dispersion force. So we have this equation that is derived from the derivation of the Reynolds average that I showed you before. And if you want, I'll show it again. So this is the way we introduce this effect of the turbulent dispersion. Is a formulation of this turbulent dispersion force that is due to Barnes. It's very well known, and this is actually a function of the gradient of the volume fraction of the solid and of the liquid phase of the slip velocity. And as you see here, we have the same equation for drag and turbulence, apart from the fact that here you have the slip and here we have the gradient of the volume fraction. I don't know if this reply to
Yes, it was okay. I have another question. Did you work with the Lagrangian also or not? It was purely Eulerian and Eulerian methods.
I've presented you results also only in the Eulerian case. We consider this considering that we have often very high volume fraction of the dispersed phase of interest in industrial application, and we have considered the Eulerian approach suitable, but I don't exclude that also with the Lagrangian case, with the Lagrangian model for the dispersed phase, you can get good results, but it's not something that
I totally agree. I totally agree with you with a rough answer. Yes, and Eulerian is better, but if you want get the detail about the particle and droplet, bubble interaction, you need, for example, in the shear flow, you need using the Eulerian and also Lagrangian. And I have a question about the using your methods. You use the Eulerian. And also you model bubble and particle also, right?
Yes.
How you handle the interaction between the bubble and the particle? Because we know that the Rushton turbine use it for separation, the mineral material also, and the hydrophobic particles from the below of this turbine, right? How you handle the interaction between the interface of bubble and particle? Did you consider another forces for that or not?
So far, we didn't go into this very complex problem. Actually, at the moment, I'm involved in a project where we have a three-phase reactor, so gas, solid, liquid. But since the dispersed phase, the solid dispersed phase is very, very fine, we are considering the solid liquid system as a pseudo single phase system with a suitable viscosity. So what you are interested in is very, very, very complex. I think it would be more important to actually perform a simulation of this system in a much simpler geometry. So having a fundamental study on these forces and interaction, and then feed them in a simplified way in the lab scale or industrial scale reactor, because this physical systems, I think it is hardly.
I think
it's hard to describe. Too much complicated physics. So, but it's not something that I physiced so far. So, it would be very interesting to investigate.
So, how you can calculate the separation rate without considering these forces?
Excuse me. Yeah, I think, thank you very much, Sajjad, for asking this question. Very interesting, I must admit. The thing is, we are behind schedule. So I think relatively long behind schedule now. So in the interest of the community attending the meeting, I suggest if you have any more question to write an email to Professor Montante. I'm sure she will be happy to answer your question.
Okay,
sorry,
thank you.
Sorry
thank you.
Thank you very much for your questions and for the interest. Thank you.
Thank you.
Okay, so let's, I hope you will join me in thanking Professor Montante for his very, very interesting talk and for the discussion that came out of